Welcome guys. In this video, we're going to be solving this very problem. And for this very one, it says, find the Fourier series expansion of the function. So we have the very function right there. I'm Dr. Avitech, and on my channel, we deal with engineering and mathematics problems. So for us to get started, remember to hit the subscribe button, like this video, and share it across to your classmates. So for a start, remember that when dealing with Fourier series, you need to find the Fourier series coefficients. So that's A naught, A sub n, and B sub n. So let's get started with A naught. To find A naught, it's actually an easy one. The period here is 2 pi. So our formula is going to be A naught. This is A naught equal 1 over pi. Integral from minus pi to pi of f of x dx. Yeah, that's what our A naught would be. So A naught is actually the simplest one to find. But we know that integrals talk about areas. So we use integrals to find areas. So instead of using this integral, I prefer to just find the area after graphing the function. So because I can, listen please, because I can easily sketch that function and I feel like it's something I can find the area, I am going to just use that approach. So let me quickly sketch this function. So we're going to have something like this. Okay, yep. This is 0, this is minus pi, and this is pi. Just a quick sketch so I have a picture of what the area would look like. Okay, so right now, from minus pi to 0, it was at 1. So let me put 1 right here. So from minus pi, okay, from minus pi to 0, it was at 1. So I've graphed that one. Then from 0 to pi, it was at x. Now, since we just have x, this tells me that since f of x is equal to x, this means whatever x is what the function would be. And remember that I've done a video on how to graph functions, right? Or on how to sketch functions. So it's just going to be a straight line where at 0, the f of x will still be 0. At pi, f of x will still be pi. So we're kind of having something like this. Is what we're having if we kind of grab the function very fast. Okay, so let's find the area of these two parts. So the area of this guy, this is a rectangle, right? So area is length times breadth. From here to here is pi because we have 0 to minus pi. But we can't say minus pi because distance is always positive. So from here to here is pi. So this is pi. Then here to here is 1. Here to here is 1. So what is the area? Area is length times breadth. So what is pi times 1? Pi times 1 is pi. So the area of this rectangle is pi. Now how about this one? This is a triangle. An area of a triangle is half base times height. So we're going to say this is half BH. So what's the base? The base is pi because from 0 to this is pi. This is pi. Then what's the height? How high did it go? So it's pi. The height of this is pi. Because when you trace it properly, you should have pi. Okay. So this will then become half pi squared. So the area of this part is half pi squared. So I kind of feel this is better. So A naught will then become 1 over pi. This whole integral here is then our area. So and our area will become pi plus half pi squared. So I just prefer this one. You can still use the integral, please. You can still use the integral, but I don't want to do that. So this is 1 over pi. 1 over pi will multiply these two sides. So this is 1 over pi times pi plus 1 over pi times half pi squared. So we're going to be left with when pi cancels pi, that's 1. When pi cancels pi here, this will be pi over 2. So that's just it. Yeah. So even if you use this, your answer will still be the same. So I don't want to go through that. That's why I did that. Okay. So the next one will be A sub n. But I think there should be one video where I solved it like this. Because there are times where I can't really find the area. So the reason I did this is because I know that the shape is something I can find the area. So that's why I used it. If it wasn't possible, what I would do is the integral of this within this interval plus the integral of this within this interval, my answer will still be correct. So a sub n is 1 over pi integral from minus pi to pi of f of x cos nx dx. Now remember to always identify what formula you're using. Okay, now the thing is, let me roll this here. There was no single function value in our equation that ran from minus pi to pi. If you look at this correctly, no value is from minus pi to pi, no single value. Instead, we have minus pi to 0 first, then 0 to pi. So what I would do is to say this is 1 over pi, open up a bracket, and this will be integral from minus pi to 0, because that's the first one, minus pi to 0, and the function was 1, so f of s was 1. Then you say cos nx dx plus the next integral will be from 0 to pi, and the function was x. When it was 0 to pi, the function was x, cos nx dx. Okay, so that's all we have. Beautiful one. Okay, so this will be 1 over pi. Then we're going to say, well, we know that 1 times anything is that same thing, so that's not really a problem for us. So let's integrate cosine of nx. To integrate cos, we're going to have sine. So this is sine nx. And this would be from minus pi to 0. Yeah, if you integrate cosine, you just get sine. But always remember, you see, I almost forgot to put the division by n. So you must always divide by the derivative of nx. It's a must. You must always divide by the derivative of nx. So that's why we have that. Plus, now, this is x cos nx. We know that when you're dealing with integration and you have two functions in x, you need to use integration by parts. But the thing is, I am not going to do that because that's going to take me some time. So instead, what I will use here is a shorter approach, which is still the same basically. So I'm going to write x. This is the procedure. I'm going to write x. So after writing x, I'm going to differentiate x, give some space and differentiate x. I'm going to get 1. Now, since I'm done with the x, let me go to the cos nx. The cos nx, I'm going to integrate cos nx. So to integrate cosine, I'm going to have sine. This is sine nx divided by the derivative, that's over n. And this very bracket you see here, I'm going to integrate this again for 1. I'm going to integrate this value for 1 again. So integrate this value again for 1, I'll say times. The sine will give me a minus cosine. When I integrate sine, I'm going to get minus cos nx. Then, when I differentiate the angle, I'm going to get n. But since this whole thing is what I'm supposed to integrate here, it means there has been an n before. So if I'm integrating this again, from the derivative of nx, there's going to be an n coming to meet this n. So that's n squared. Now, please take note, if you use integration by parts, you could do that quickly. Your answer will still be the same. The reason I do this, and I want to keep on doing it, is so that you master it. And with time, you're going to be able to solve some harder problems. Imagine if we have x squared here. Using integration by parts will be a lot more tedious. Like, this is still integration by parts, but writing the formula will be much more tedious. So what we then do next is, this first part is always positive, so this is positive and this is negative. Yeah. And then our limit for these two would be 0 to pi. So we have 0 to pi. Okay. Now, let's simplify where possible. Let's just simplify where possible. So this is 1 over pi. I advise you to start watching the videos from the playlist so you understand every single thing about Fourier. So this is sine nx divided by n from minus pi to 0 plus, this would just be x sine nx divided by n. Let me put the limits for it here, close to it, 0 to pi. Minus times minus is plus. So this is cosine of nx divided by n squared from 0 to pi. Now, in the previous video, we've been able to ascertain that When you're dealing with sine, if you put the angle 0 or put the angle minus pi, you will get 0. Because sine 0 is equal to 0, sine n pi is equal to 0, sine of minus n pi is equal to 0. So you can see that all of these are just zeros. So what this tells me is, provided there's a sine here and these are my limits, everything here will be 0. This is also sine. My limits pi to 0, this would also be 0. So those two guys are eliminated. So the only useful one becomes this guy. Okay, so this will become 1 over pi. Then we have that, so that's cosine of nx over n squared from 0 to pi. Now the n squared is common, so I could kind of bring it out. So let's bring this out. So this will be 1 over n squared pi. Then we have cosine of nx from 0 to pi. All right. Next, this is 1 over n squared pi. Then cosine of nx. Anywhere I see x, I'm going to be putting pi. So this will be cos n pi minus cos 0. Because when you put in x here as 0, n times 0 is 0. So you kind of get the picture. So this is 1 over n squared pi. Now the special values here, cos n pi is equal to minus 1 to the power of n. It's a special value. Then cos 0 is equal to 1. So cos 0 is equal to 1. So cos n pi is minus 1 to the power of n. And then minus cos 0 is 1. And the good thing about this very expression is this very expression can be 0 at times and it could be a number at times. So sometimes you might want to simplify this whole, because our main aim is to make sure that we simplify very well before we then get the Fourier series expansion. So let's try to simplify this very, very well. So to start with, this bracket, I noticed that something can happen with it depending on the type of number I have, depending on the type of number we have. So we're going to say it's not a crime to leave it like this. But the thing is, when you are finally evaluating your Fourier series, you try your best to make sure that life is easy. Otherwise, it's going to get bulky there. So we'll say when n is even. Let's start from when it's even. Let's see how it behaves when the number is an even number. Because Fourier series is an infinite sum. So you'll be putting n equal to 1, n equal to 2, n equal to 3, different numbers like that. So the numbers you'll be putting are either even or odd. And the behavior of this will differ if it is even or if it is odd. So let's start with when it's even. So we know that minus 1 to the power of n minus 1 is the expression that we're trying to find out how it behaves. So this will be minus 1 to the power of, pick an even number for n. Let's say square minus 1. Now minus 1 to the power of 2 is 1. And then you have minus 1. So this is 0. So what this means is n is even. When n is even, you're going to be getting this bracket as 0. Now, if this bracket is 0, that means that a sub n, which we've been looking for, a sub n would then become 1 over n squared pi times 0, because this is 0. So everything here becomes 0. So you can see that it now lets us know that instead of us to be putting n equal to 1, n equal to 2, n equal to 3, provided we are putting 2, which is even, we'll get 0. So it helps us out to know that, oh, whenever we get an even result, we don't just put it because it's going to be 0 at the end of the day. There's a lot of stressing us there. Let's know that it's good we know the information now than to know it in the future. So currently, when n is even, we know that a sub n is 0. So we don't need to write when n is even. And let's find out when n is odd. Yeah, I think I can do it here. So when n is odd, so this is minus 1 to the power of n minus 1 equal to minus 1. Let's pick an odd number. Let's say 1 minus. Please take note, any odd number you pick, the result will still be the same. So minus 1 to the power of 1 is minus 1. Then you have minus 1. So minus 1 is minus 2. So you can say this one is not 0. So this means that your a sub n would then become 1 over n squared pi, your a sub n, 1 over n squared pi, and then these brackets. But when it's odd, this bracket is equal to minus 2. So times minus 2. So this will be minus 2 over n squared pi. So this is when n is odd. And this when n is even. So life is kind of better. Life is kind of better if you actually know this. So let me keep this information somewhere here. Let me keep the information somewhere here. Okay, so first of all, a naught is 1 plus pi over 2. That's a naught. A sub n is minus 2 divided by n squared pi. This is when n is odd. Or you could say then it's equal to 0 when n is even. This is not really relevant. You just have to keep this at the back of your mind. The 0 part is not really relevant. Now let's find b sub n. Remember to hit the subscribe button and like this video. All right, so for b sub n is 1 over pi, integral from minus pi to pi of f of x sine nx dx. So that's your b sub n. And for this one, it's still kind of the same. The minus pi to pi will be broken down to minus pi to 0 and 0 to pi. So let's break that down. So this will be 1 over pi integral from, the first one is minus pi to 0. Minus pi to 0. And f of x was 1. So this is 1 sine nx dx. And then plus, okay. And then plus the integral from 0 to pi of our f of x this time around was just x. This will be x sine nx dx. And I'm going to close this up. All right. So this is the time for us to integrate. So this will become 1 over pi. And then let me open this up. Now I know that 1 times anything is that same thing, right? So this is just sine x. So let's integrate sine x. So to integrate sine, we're going to have minus cosine nx. Then divide by the derivative of nx. So differentiate nx, so we get n. Then you put your limit, minus pi to 0. So that's the first one. That's the first one. And then plus. This is integration by parts, but the first thing I want to do is to use a shortcut. It's not really a shortcut, but it's still the same. I'm going to write x down. So write x down. Then give some space. Differentiate x, I'm going to get 1. So this is when you pick your x, you start differentiating x until you get to 0. Then you stop. But as you can see, when I get to 1, if I differentiate and get 0, I'm not going to write the 0 because I know that 0 will just give me nothing. So I did not write that. But for the sine, let us now integrate sine. So we pick this x and differentiate x. Then for the sine nx, we integrate it. So integrate sine. To integrate sine, we're going to get minus cos nx. Then divide by the derivative of nx, that's n. Now every single thing in this bracket, you're going to integrate it again. So integrate this. Integrate this. First of all, there's a minus. There's a minus. And then cosine will give us sine nx. Now, when you differentiate the nx, you're going to have n. Now, since there was an n before, and it's everything here that we are integrating. So there's been an n before, and when integrating the cos nx, there was another n. So n times n here will give us n squared. Give us n squared. Then this one is plus, this one is minus. You must always do it like that, plus minus. Reason is, remember that integration by parts, integral of u dv is equal to uv minus integral of v du. So this is always positive, this is negative. So that's why it's like that. So this positive, this negative, just like that. So the limits for this one is 0 to pi. 0 to pi. All right, let's simplify our expression. So this is 1 over pi minus cos nx over n from minus pi to 0. And then plus times minus here will give me minus. Give me minus. So this will be minus x cos nx over n. So the limit for this is the 0 to pi. So let me put 0 to pi. And then minus times minus will give me plus sine nx all over n squared. And then 0 to pi. All right. So this is what we have. Okay. Now already, we know that whenever we're dealing with trig expressions, this guy you see here, every single part of it is 0. Every single part is 0. So what it means is this guy will be 0. So no need for me to really stress myself about this, because sine n pi is 0. Sine 0 will still be 0. So that guy is gone. So the only useful one is this. So let's kind of find a way to do this. Okay. So for us to get started, since these are the two guys that we have, you first have to know that the over pi is common between these two things. So since it's common between these two things, you can, factor it out. You could bring it outside. Also, I can still do this. Minus is here, minus is here. So I can still bring out the minus since I'm dealing with just these two. So this will become minus 1 over n pi, because the n is also coming out. So what will be remaining will then become cos nx from minus pi to 0 plus, remember I brought out the two negatives. So when you do that, it means everything will now be positive. So this is s cos nx from 0 to pi. It's looking much more beautiful now. So this will be minus 1 over n pi. And then let's put in our limits. So this will be cos 0, because n times 0 is still 0. And then minus cos, put in minus pi here. But here's the thing, cosine is an even function. So even if you put in a negative angle, it's still the same as saying n pi. If you put in minus n pi, it's still the same. I think in previous examples, I've been able to explain this, that if you put in a negative angle into cosine, it's still the same with when it's positive. So instead of me writing a minus n pi here, let me just put n pi because I know it's the same. And I've told you also that's the same. So I think I'm going to make a video soon on even and odd functions. So the next one, so should I put a bracket? Not really necessary. So this is the first one. And then plus. The next one, I'm going to put x as pi. So this is x, so this will be pi cos n pi. And then minus for the lower limit, of this part. And if I see x, s will be 0. So this will be 0 cos 0. Yeah, but the thing is, this part will just be 0 because 0 times anything is 0. So this guy is gone. That guy is gone. Let's proceed. So this is minus 1 over n pi. Cos 0 is 1, special angle. It's 1. Minus cos n pi. This is minus 1 to the power of n. That's minus 1 to the power of n. Plus, this one right here, this is pi. Cos n pi again is minus 1 to the power of n. This is a lot. This right here is a lot. All right. Let's see. Oh, never knew this beautiful expression would exist. Okay, let's proceed. The thing I want to do, or what I want to do next, is this expression here could have even and odd guys. So my expression could be a lot more easier. Yeah, a lot more easier if I have even and if I have odd. This is looking bulky. Yeah, there are too many things in that bracket. So let me find the behavior of this when n is even and when n is odd. But I can from here to get it though. I can from here to get it because this minus 1 n minus 1 is looking like this one, just that I have to multiply by a negative number. But let's not go into that. So I'm going to say when n is odd. Let's kind of start with that one. Let's start with that one when n is odd. So I want to deal with the brackets first. So we have 1 minus 1 to the power of n plus pi minus 1 to the power of n. Okay, so for this one, n is odd, right? So we're going to pick n as 1. Let's pick n as 1. So this should be 1 minus 1 to the power of 1 plus pi minus 1 to the power of 1. So this is 1 minus n to the power of 1 is that same thing. So this will still be minus 1. And then plus pi, this will still be minus 1. So this is minus minus will give me plus. So this is 1 plus 1. And then this one right here, this will be giving me minus pi. So this will then become 2 minus pi. So this is my expression for the bracket when n is odd. So let me come back to this. So this means that b sub n would then become minus 1 over n pi times, this is what the bracket will be, 2 minus pi. So we have 2 minus pi. Okay. So when you multiply the top, minus 1 times 2 minus pi will give me pi minus 2. Let me kind of write it here. This is equal to minus 1 times 2 minus pi will give me pi minus 2 divided by n pi. Now, how was I able to do this? Minus 1 times minus pi is pi. Then minus 1 times 2 is minus 2. So I kind of just, because the negative would kind of flip these two guys. So that was what I just did. So this is my b sub n. When n is odd, of course. When n is odd. So it's looking like a very bulky expression. So this is what it is. So that's b sub n. Now the next thing I want to do is when n, let me write it here. So b sub n is pi minus 2 divided by n pi when n is odd. Okay, when n is odd. So the next one is when n is even. When n is even. Because believe me, this whole expression is too bulky for you to put into the Fourier series expansion formula. So it's too bulky. So we're trying to, reduce it. So we have 1 minus 1 to the power of n plus pi minus 1 to the power of n. So the even number we're going to pick, let's pick 2. So this is 1 minus 1 to the power of 2 plus pi minus 1 to the power of 2. So this is 1 minus 1 squared. When you square a number, a real number, you're going to get 1. And then plus pi, this one here, when you square this would also be 1. So 1 minus 1 is 0, so this guy is gone, just straight away. Then pi times 1 is just pi. So you can see the bracket is just pi this time around. So this means that b sub n is equal the coefficient outside minus 1 over n pi times this whole bracket is giving us pi. So when pi cancels out pi, we're just going to be having minus 1 over n. So this is when n is even. Abi? Yeah, when n is even. So b sub n is minus 1 over n when n is even. Yeah, because this guy is actually very, very large for me to be writing. It's large, so I don't want to do that. Okay, so this is now the time for us to get our Fourier series, the expression for the Fourier series of this function. So let me wipe this board. So this is the time for us to get the Fourier series of the expression. So f of x, the formula for this, f of x is equal a naught over 2 plus the sum from n equal to 1 to infinity of a sub n cos nx plus the sum from n equal to 1 to infinity of b sub n sine nx. So this is what we have. Sorry. Okay. So right now, let's put it in. Let's get started. So I know that my b sub n, I want to split b sub n into 2 in such a way that we're going to have odd and even. So let's split b sub n. So I'm going to leave the a naught over 2 like that plus the sum from n equal to 1 to infinity. I'm going to also leave a sub n like that. But this one, I'm going to write 2 of them. So this is the sum from n equal to 1 to infinity of b sub n sine nx. So I'm going to just put even here. I'm going to put, okay, since odd is the first, let me write odd. So when it's odd, plus the sum from n equal to 1, then this will be even, to infinity of b sub n sine nx. Okay, and the thing is, most times, some persons might forget. It's not intentional. Some persons might forget that they wrote odd and they wrote even. So there's a way to actually know. There's a way to actually know that the expression will be odd throughout. So there's a way to write your n in such a way that the expression must be odd throughout. Now, a sub n 2 must always be odd too. So put odd here. Now, here's the thing. Here's the thing. Take note of this. Yeah, let me write it here. If you need an expression that is always even, replace your n with 2n. If you need an expression that is always even, replace your n with 2n. So always, this is always even. 2n is always even. Now, if you need an expression that is always odd, replace your n with 2n minus 1. This is always odd. So that's what you do. Yeah. So let me effect this change. Do please take note. It's not all, should I say, lecturers or professors that would be writing these two. They could just still leave everything like this. It's still going to be the same, please. It's still going to be the same. So let me put in what my a naught is. So a naught is 1 plus pi over 2. Now here's the thing. Your a naught is also being divided by 2. So what would I do? I would divide these two terms with 2. So divide these two with 2. So I'm going to say 1 over 2 plus, that's pi over 2. So if you divide pi over 2 by 2 again, that will be pi over 4. I believe that's understandable. You divide the two of them by 2. Plus, and this very one here is the sum from n equal to 1 to infinity. A sub n is, where is it? Okay, this guy said where is you? So that's minus 2 all over n squared pi. Okay, and then you put your cos nx. As you can see, you have to remember, for me, I basically don't do I have to remember. I would always just turn the n to odd. So that even if I make a mistake and I put a number for n, that number will still be, the result will still be n at the end of the day. But let me leave it like this, since most books that I've been seeing, they kind of leave the answers like that. And then plus, for this very one, the sum from n equal to 1 to infinity, b sub n when it's odd, b sub n is pi minus 2 over n pi. And then I'm going to put sine nx plus, this is a lot. Okay, the sum from n equal to 1 to infinity, b sub n when it's even is minus 1 over n sine nx. All right. So the thing is, like I said, you can just forget, and it's a very, very disappointing mistake to make, that you then forget that this one must be even. Unless, of course, you have to be coming back to look at this every time. Okay, so let's proceed. I will still write it the way I want to write it. I will still put this thing because I don't really want to make that mistake. So this is half plus pi over 4 plus, if you look at this, there's a constant here. The sum is with respect to n. The sum is with respect to n. So anything that does not have n is a constant. So minus 2 over pi, minus 2 over pi has to be a constant. Minus 2 over pi has to be a constant. So bring it outside. So this is minus 2 over pi. It's a constant. And then we're going to have this sum from n equal to 1 to infinity. What will be left will then become 1 over n squared. Because the minus 2 over pi is gone. So what will be left is, because there must be a numerator. So this is 1 over n squared. Cosine of nx. Now this one, what will be the constant here? The constant will be pi minus 2 over n. Sorry, over pi. Because this is with respect to n. So it's pi over 2 over pi. So this will be plus pi over 2 over pi. Then the sum from n equal to 1 to infinity of what will be left to then become 1 over n sine nx. And then this one here, this is minus. So I want to bring out the minus. So this is minus the sum from n equal to 1 to infinity of 1 over n sine nx. It's not looking as if these two things have something similar. But please do not forget that there's a multiple here for this first one. Okay. Now, if I leave my expression like this ought to be the Fourier series, but I need to then indicate that, okay, this one is odd, then this one is even. So this is where I then do what I want to do, please. I have to put this guy so that I wouldn't make a mistake. So this will be, okay, f of x, f of x, f of x, f of x. So this is half plus pi over 4. Then this whole thing here is minus 2 over pi. Then the sum from n equal to 1 to infinity. And the next thing I'm going to do is, this will be 1 over, I know that my n, everything here is odd. So when it's odd, it's 2n minus 1. So this n here will be 2n minus 1 all squared. This way I would always remember that this would be odd, because no matter the value of n you put here, this whole thing will be odd. And then cosine of the n here will become 2n minus 1 x plus pi minus 2 over pi, then the sum from n equal to 1 to infinity of 1 over, this is also odd. Yeah, this is also odd. So the n here will be 2n minus 1 sine of 2n minus 1x. This is a lot. Okay. And then plus, the last part is a minus, because I've not written that part. So that's a minus the sum from n equal to 1 to infinity of, this expression will become 1 over 2n, because this has to always be even. 1 over 2n sine 2nx. All right. Now, if my equation tells me that I should leave my answer in terms of n, this will be my answer. If it's in terms of n, this will be my answer in terms of n. But let us write some things. Let us write some terms. So let us say let n be equal to 1 in all of this expression. So this is my answer if they say leave my answer in terms of n. But let us put some numbers in, because sometimes you can be asked to put in your numbers, but you cannot really go to infinity. So you just have to do some things. So this will be half plus pi over 4 minus 2 over pi. Then this whole summation here, let us write out some things. Let us write out some things in this summation. So open up a bracket. Now, like I said, you could decide to use this one or use the one at the top. So most persons are used to using this one at the top. But like I said, you just have to remember which one is odd and which one is even. So since I want to use the one at the top. So this one at the top here, we know that n is going to be odd, right? So let's pick 1 as the first one. So everything here will just be cos x. Everything will just be cos x. And then plus, what's the next odd number? 3. The next odd number is 3. So we have 1 over 3 squared. So that's 1 over 9. 1 over 9 cos 3x. The next odd number will be 5. So this will be 1 over 25. Because if you say 5 squared, that will be 25. So that's 25 cosine of 5x. Now, do you know that if you even wish to use this one that I used, your answer will still be the same. So let's put n equal to 1. So we should put 1 here. 2 times 1 is 2. 2 minus 1 is 1. And 1 squared is 1. So 1 over 1 is 1 times cosine of 1x, which is still cos x. So it's still the same. If we should put n as 2, like I said, for this very one, you don't really need to bother yourself which one is even or which one is odd. Because by putting these substitutions, you will definitely be getting the right answer. So put in n equal to 2. So when you put 2 here, 2 times 2 is 4. 4 minus 1 is 3. 3 squared is 9. So this is now 1 over 9 cos 3x. Now, the next one, when n is 3, when you put in 3 here, 2 times 3 is 6. 6 minus 1 is 5. Now, what is 5 squared? 5 squared is 25. So you see that that one will just give you one answer throughout. Plus, you cannot really go to infinity, so you just need to end somewhere. So I've done that. Plus, now this next one here, this is pi minus 2 over pi. Then open up a bracket. Now for this one, this is also odd. So you can decide to use this part. But this is always also odd. So you need to remember. The reason I put this one at the bottom is you might forget. So for you to remember, what you're going to say is, this will become, put in 1. So 1 over 1 sine 1x. So this will be sine x. And then plus, plus. So the next one will be 3. It will be 3 because this is odd. So it will be 3. But if you're using this one, you don't really need to bother yourself on which one, if it's 3 or not. So put in 3. So this will be 1 over 3 sine 3x. So what's the next odd number? 5. So that's 1 over 5 sine 5x. Next odd number, 7. So that's 1 over 7, just like that. But we can't really get to infinity, so you need to end that. So the next one, this is the next 10. That's this last one here. This last one. That's what it is. So this is minus. Open up a bracket. But this one is always even. This is always even. So this will be starting from 2. But in this place, if you should use this very expression, when you put your 1 here, 2 times 1 is 2. So you must always be having even. But let's use this one. So put in your 2, since we're dealing with even numbers. This will be 1 over 2 sine 2x. The next even number is 4. So this is 1 over 4 sine 4x. The next even number is 6. So this is 1 over 6 sine 6x. You can't really get to infinity, so you need to end that. Now, this will be the Fourier series expansion of this function. So this is the answer to our question. Remember to hit the subscribe button, like this video, and I'm going to see you in the next one. Bye.